Hey everyone. So in the last two videos, I kind of went through the math step by step to derive the OLS estimator. And remember, we started with specifying the sum of squared residuals across all observations, and then said, okay, we want to find the parameters that minimize those sums of squared residuals. But one question you could ask is whether that is the right strategy. Is that actually a good estimator? Why should we use OLS rather than some other estimator, for example, right? And one of the reasons that make OLS, the OLS estimator, a good estimator is that it is unbiased, right? There are a couple of other reasons and justifications that we will consider later and also in the next semester. But one most basic justification for OLS being the OLS estimator, being a very useful estimator, is that it's unbiased. What does it mean that an estimator to be unbiased? Well, it means that in expectation, the estimator is equal to the true population value, right? So if we take the expectation of our beta hat of our OLS estimator, then the expectation of that estimator across, you could think of it as across repeated sampling. If we were able to repeat our survey 1,000 times or a million times, or our data collection, it doesn't have to be a survey, it could be our data collection procedure. If we were able to repeat this a large number of times, the average of our OLS estimators across all those separate trials would be equal to the true population value, right? So on average, we're getting it right? And so this statement of on average getting it right, getting kind of the true population parameter correct on average is a good or is a useful property for an estimator to have, right? There are other properties when it comes to kind of variance and uncertainty that we'll talk about later, but for now we'll focus on just whether in expectation we are able to retrieve the true population parameter, okay? And in order to show that OLS is indeed unbiased, so in order to show that the expectation of the OLS estimator is in fact the true population value, we need to make a couple of assumptions, right? And so in the video or in this video, what I'm going to do is I'm going to go again through the math to show that OLS is unbiased using 4 different assumptions, okay? The first one is that the true kind of underlying population model is the linear model, right? So in the population, y is a function of xn, and the relationship between y and xn can be described using this linear specification: alpha intercept plus beta times xn plus an error term epsilon, okay? The second assumption that we're going to make here is that the x's are fixed. They're not random variables, right? So we can think of, under repeated sampling, we would kind of observe the same x's for the same individual, for the same observations, right? There are, we don't necessarily need to make this assumption. You can show that OLS is unbiased without assuming that the x's are fixed, so that while kind of relaxing this assumption and allowing the x's to be random variables. But that is a little bit more complicated. We'll go through that later, probably in the next semester as well. The easier case is just assuming that these x's are fixed, which, for example, in the context of an experiment where you have control over who gets, for example, the treatment versus or who's assigned to the treatment versus the control condition, is a reasonable assumption to make. But again, we'll look at other cases with stochastic x's as well. The third assumption that we're going to make is that there's a variation in the x's. So what does it mean for there to be variation in the x's? That means that the variance of the x's, so the expectation of x squared minus the square of the expectation, square of the average, is not equal to 0, right? So there needs to be some variation in x, which makes sense, right? If all x's have the same value, you can't really estimate the effect that these x's have on some outcome y. And the fourth assumption that we're going to need is that in expectation, the error terms, or the expectation of the error terms, is equal to 0. Okay, so with those four assumptions, we can show that the OLS estimator that we derived previously is indeed an unbiased estimator of the true population beta. Okay. And we're going to start by showing this by starting with this definition or kind of looking at the expectation of beta hat as we defined it or as we derived it in the previous two videos. And then we're going to see how we can kind of simplify that expectation to arrive at the actual true population value beta. Okay. So the first step is, of course, to take the expectation of our beta hat, and for beta hat we're plugging in the formula that we derived in the previous videos, right? So that's just our sum xn minus x bar times yn minus y bar divided by the sum of xn minus x bar squared. Okay. So given the second assumption, which, if we go back, is that the x's are fixed, so they're not random variables, that basically means that we can take, if we take the expectation of a set of random, or of a set of variables, and those variables are fixed, we can basically just take all those fixed terms out of the expectation, right? So we start with the expectation of this entire term, but given that the x's are fixed, we can actually pull, kind of like pulling a constant term or a product out of the expectation. We can basically pull all this stuff out and just we're left with the expectation of yn minus y bar. Okay, and this sounds like a weird, or this might look like a strange trick. But again, keep in mind we can also arrive at the same conclusion without assuming the x's to be fixed, and we'll get to that at a later point. Okay, but for now, assuming that the x's are fixed allows us to pull them out of the expectation. If we then focus on that expectation, so this part, the expectation of yn minus y bar, we can again kind of rewrite this y bar as 1 over n times the sum of n, the index here changes from m equals 1 through n of ym. Okay, so the index here changes to not get confused with the yn here, right? So rather than writing y bar, this is just the sum of all y's divided by the number of elements in y. Okay, and then using the first assumption, which specified the true kind of linear model as the data generating process in the population, we can now plug in alpha plus beta x plus epsilon for our yn, right? So since our assumption in basically in the population holds that yn is equal to alpha plus beta xn plus epsilon n, we can plug this in for our yn here as well as our ym here. Okay, so we're ending up with this equation where we have alpha plus beta xn plus epsilon n, and the same here for ym here. Okay, so we're just plugging in our linear model as the underlying data generating process for each of those yns that we actually observe. Okay, so given that the x's are fixed, again, this is the second assumption that we used, we can again kind of reduce this expectation again, or in a sense pull out all the fixed parts out of the expectation and only focus on the the random variables inside the expectation, right? So that means alpha and beta, those are just the true population parameters, and xn, though, they can all be pulled out of the expectation, right? So comparing this to this, we see that the only place where the expectation is kind of left is the expectation of epsilon n here and the expectation of epsilon m here, okay? Again, based on the argument that the x's are fixed and alpha and beta are the true population parameters, they are fixed as well, we can pull them out of the expectation. Next, using the third assumption, which I have to look back, assumes that there is variation in the axis. So let me see real quick. This should be, sorry, this is a little mistake. A3 here should be A4, because this assumption, A4, is the assumption that the expectation of the error terms is equal to 0, right? So if the expectation of the error terms, the expectation of epsilon n is equal to 0, that means this part and this part drops out. They're equal to 0, so we're left with this equation. So in the notes here, before I upload the slides, I'll make a change here. This should be A4, okay? And then if we have that, we can basically go through or kind of evaluate this sum divided by n, which alpha is kind of similar to what we did when we derived beta hat. Summing alpha, a constant, n times, and dividing by n, that's just equal to alpha, right? So this is basically, this can just be this basically just can be pulled out, and then dividing by n, or n divided by n is 1, so this turns out to be minus alpha. And the same here with beta and xm, so the sum of all x's divided by n is of course x bar, right? So we're left with a minus alpha minus beta x bar, okay? Now, alpha minus alpha of course cancels out, and then we can multiply out this beta to get beta times xn minus x bar. And now plugging this back into, remember that we started, if I go back a little bit, we focused on this expectation of yn minus y bar, right? So this part. And so now we found an expression for that, and we're going to plug that back in to this initial equation, okay? So if we plug this back in, beta xn minus x bar, we plug that up up here, we get this expression. We can move the beta in front of the sum. This is again just a constant that we can move in front of that sum. So this turns out to be beta times sum from n equals 1 to capital N of xn minus x bar. And now note that this xn minus x bar multiplied can just be written as xn minus x bar squared, which means that the numerator and the denominator are exactly the same, or outside of that beta. These two parts cancel out, so ultimately all that we're left with is beta. And this is already what we wanted to show. The expectation of beta hat is equal to beta, and so in conclusion, we thereby showed that OLS is unbiased.